Okay, I appreciate that you're here on a date that's immediately after the exam, and it's the Friday before spring break. So what I plan on doing today is, besides answering any questions you might have about the class, is to go over the exam you just had. Okay, so you can, the grading process will take up the next at least 3 to 4 days, if not more. Okay, so you'll get the results back the first Monday we come back from spring break. Okay, but I thought, since you still probably remember some of the questions you saw on the exam, so I could just go ahead and discuss with you the correct answers, okay, to the exam questions. Okay, and give you a chance to ask any question. Like if you have a slightly different answer, but you think your answer should be equally as acceptable, then mention it to me, because the grading, like I said, is still in progress. So what you said today might influence the way that you are being graded. Of course, even after you're being graded, you can still bring up any concern you have about the grading, because I was a little surprised that no one actually said anything about the first exam, either because the grading was done so perfectly that no one had any complaint, other than 1 or 2 students who had the score added up wrong. A person who had a 60 on the first page of the exam, okay, end up having 70 because 10 points was not being added properly. Okay, so other than those minor, computational or addition errors, no one had complained about the grading on the first exam. So I was very surprised. But maybe it's not just a matter of complaining, but if you feel like you are being graded unfairly, then you should say something about it. Okay, so let's go to your questions first. Do you have any questions from the lab, I guess? Because ever since you had the exam, we had not had any lecture, but there is a lab. Okay, do you have any questions from the gas law experiment? You understand that experiment? Okay. All right, so if that's the case, then I'll just go directly into discussing the exam, okay? And I'll start with, well, let me just describe it to you once again. There were 2 different versions of the exam, okay? Version number 1 has, questions problems 1 through 7, okay? And version number 2 had a slightly different problem number 1, okay? And then the rest of the problems were basically scrambled. So, problem number 2 on version number 1 may not be the same problem number 2 on version number 2, but essentially every student sees the same set of questions, just in different orders, except for problem number 1, where I actually created 2 alternatives. Okay, so I can tell you exactly what those alternatives were. I thought I brought some markers. Okay. Well, hopefully these works. Okay, so it should be okay. All right, so problem number 1 on the second exam basically asks you to supply all the missing data in the following table. And the table looked like this. It has 5 columns. Okay, so the first column is for the symbol and also the mass number. Okay, so it's not just the symbol of the element or the isotope, but also the mass number. I give an example of what I meant by this. So example was the C14. So you have a symbol for the element, and that's carbon. Okay, and the 14 stands for what? It stands for the mass number. Okay, and then the next column is the atomic number, Z. And then the next column is the number of protons. So I spell it all out, number of protons. Okay, and then the next column is the number of neutrons. Number of neutrons. And then finally, the number of electrons. Okay, so how does it work? Well, okay, given one piece of information, okay, the idea is you should be able to kind of, look at it as a puzzle. Okay, you're given a clue. So, go figure out the other things, right? Go figure out what should be under the other columns, okay? In fact, the only thing I need to tell you is the symbol of the element as well as the mass number. And you should be able to fill out the other 4 columns. But I guess the last column, especially the total number of electrons, I just don't want to make any assumptions. So on the first version of the exam, you would have 6, 1, 35, okay, 53, and I think 27. Okay, so I just gave you the last column. So there's no need for you to figure out the total number of electrons for any of these isotopes. Okay, so the only other columns that you need to fill in are Z, which is the symbol for atomic number. Okay, the number of protons as well as the number of neutrons. Okay, so like I said, given the C14, you should be able to determine all these. Okay, you don't need any other pieces of information. So the example has this being 6. Okay, and this is 6 because of the atomic number of carbon. Okay, I looked up carbon on the periodic table of the elements, and it would tell me, okay, carbon is number 6, element number 6 on the periodic table. Okay, every element has a unique atomic number. There's no repeat. I mean, you're not going to see carbon and nitrogen having the same atomic number because that makes no sense. Okay, every element is unique. Every element has a different number of protons. Okay, in the nucleus. So the number of protons should match the atomic number. And so just to finish this up, okay, the mass number here tells us the total number of nucleons. Okay, a nucleon means the number of protons and neutrons added together. So if these two must add to 14, what should this number be? Yeah, it should be 8, right? Okay, so this is what I gave you as an example. And I expect you to, on the exam, okay, that you took, to be able to supply, some missing cells in the rest of the column. So for the second row of the table, I just gave you this and this, and that's it. Ask you to fill out the rest of the cells. This one, I gave you 35 and 46, okay, and expect you to do the rest. And then this one here, I just give the I-131 isotope, and then the cobalt 59 isotope. Okay? All right, so what are the correct answers? Okay, well, on the exam, I gave a hint. Actually it's not hint, it's note. But the note is that in supplying the missing data, you should work row by row. So don't add the columns, okay? Because the columns don't make any sense, right? I mean, why would you add all these together? Okay, because I don't know, maybe you are so used to seeing Excel spreadsheets or something like that, that you assume, okay, well, I see a column, I'm going to add the numbers or something like that. These are all independent, independent problems. Okay, each row is a new problem, so don't ever add vertically. Okay, the table is only for my convenience in grading, so it's easier for us to, just look for the information either vertically or horizontally. It has nothing to do with, the chemistry that I'm asking you to understand. So here, the number of protons always match the number of, I guess this pen is not going to work. Okay. And like I said, I think I brought 2 dark markers that I don't know where they disappeared. Okay, well anyway, so this column here, the number of protons, should always match the atomic number because they mean the same thing. So you should put a 1 here. Okay, and if you walk, backward, and try to figure out which isotope it is. Okay? There's only one element with one proton in the nucleus. And there's only one element with atomic number 1, which is hydrogen. So this has to be hydrogen. There's no other element. Okay? Now, the mass number is what? Okay? Well, the mass number is always these two added together, the number of protons and the number of neutrons. So it's 1 plus 1, which is 2. So the correct answer is H2 and the 1 over here. Now, for the next isotope, okay, again, the number of protons should always match the atomic number. So it's 35, okay? And the number of neutrons is 46. So 35 plus 46 is 81. Okay, so the mass number, whatever this is, should be 81. Now, if you look at 35, okay, which element has the atomic number 35? It's bromine. So it's Br81. Okay, so it's Br81 and 35 over here. I-131, okay, what is the atomic number of I? Okay, so it's iodide. Some pronounce iodine. And let's see, do I have a periodic table here? Maybe not. Okay, can you help me out here? Because I'm actually looking at just blank sheets of papers. I don't have any answers.
53.
53? Is it? Yeah. Okay, so 53. Right, so just look up the atomic number of iodide. It's 53. Okay? Now, the number of protons is always the same as the atomic number, so that's also 53. What about the number of neutrons? Okay, well, that's the difference between 131 and 53. So, so what's 131 minus 53? 78. Okay. Let's see. Yeah, that's right. That's right. Okay, so 78. So the correct answer should be 53, 53, and 78. Okay, cobalt 59. Okay, what's the atomic number of cobalt? Okay, again, you need to look at the periodic table to determine this. So it's 27. Okay, the number of protons should match the number of the number of protons should match the atomic number. So it's 27 and 27. This one right here is the difference between 59 and 27. So it's going to be what? 32? Okay, make any sense to you? Okay, so if you give me all these numbers, then you should pick up all 10 points. This is a 10 points question. The alternative version, the other version of the exam, would have a slightly different question 2, I guess. Okay, the second row of version number 2 is slightly different. So I changed this to a 2. Okay? So how is that going to affect the answer? Well, no change over here because the atomic number is always the number of protons. Doesn't matter what the number of neutrons is. However, okay, once you decided that this is hydrogen, okay, the number of protons plus neutrons is not 2 anymore, it's 3. So you actually have H3 instead of H2. But of course, you don't see the 2 different versions of the exam. So the only concern you should have is, whether you add the protons and neutrons together properly to give you the H3, okay, or to give you the mass number of 3. And I think I also changed this one, so I have to erase this whole, the entire row. Okay, so I actually changed this to potassium 40. I mean, on this alternative version of the exam, this was given as potassium 40, K40. Okay, and then I think this was given as 19, doesn't matter. Okay, so what should be the atomic number of potassium? Okay, so you look that up on the periodic table, it should be 19. Okay, so this is just a matter of looking up the element potassium. Okay, and looking for that piece of information, which is called the atomic number. Number of protons always the same as the atomic number, so this is also 19. And the number of neutron is, you do the math? 31? 21, yeah, 21. Yeah. Okay, so not too bad, right? The two versions are fairly similar. Okay, so this is number 1, 10 points, because every cell is worth 1 point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 points. Okay, so this is problem number 1, just to get you to think about the nuclear structure of an atom. Okay, number 2. Okay, well, depending on which version of the exam, but I'm just going to follow one, okay? Because the other version will just have the same question appearing a little later on the exam. But on this particular version, version 1 of the exam, problem number 2 look like this. Okay, let me see. Okay, it asks for your answer to 2 different questions. Okay, so part A, problem number 2, part A, okay, it says, what can you say about the mass and volume of the atomic nucleus relative to the mass and volume of the atom itself, respectively? Okay, so there are 2 questions. One is the mass of the nucleus. So, for those of you who are really, organized, I guess, then you would want to create a 2-by-2 table, right? Something like this. Okay, I mean, you don't have to. I mean, the problem never asks you to create this table, but it's basically comparing the mass of the atomic nucleus. So I put the nucleus here in one column, and the mass of the entire atom. Again, I'm testing what? I'm testing your mental awareness of the structure of an atom, right? Previously, I just asked you to count the number of protons and neutrons in the nucleus. Okay? Now I'm asking you to compare the size of the nucleus, volume, the size. I'm asking you to compare the size of the nucleus relative to the size of the atom, and also compare the size of the mass of the atom compared to the mass of the nucleus. Okay? And so the atom is, maybe about this big, and the nucleus, I mean, this is an exaggeration, really. If the atom is only this big, the nucleus shouldn't be, the nucleus should be less size than this dot. Okay? Because if the atom is only this big, then the nucleus should be, just a fraction of this, yeah, almost nothing. Okay? That's the size of the nucleus compared to the size of the atom. So my first question is just to get you thinking, okay, how do you compare the mass of the atomic nucleus to the mass of the atom? Okay? Well, the thing is, if you know what's going on, okay, most of the atom, okay, or most of the volume of the atom is occupied by what? The electrons, right? Okay, so this is where you're going to find, negative charges. Okay, not necessarily, these electrons like particles. Okay, but just negative charges everywhere. Okay, but since electrons have very little mass, okay, every electron, doesn't matter how many you have in the atom, every electron has negligible mass. All the mass of the atom comes from the nucleus. So I would say, if you ask me for the mass of the nucleus and the mass of the atom, okay, they're about the same. Doesn't matter, okay, because most of the mass of the atom comes from the nucleus. Okay, so same mass, okay, whether you're looking at the nucleus of the atom or the whole atom. But the volume of the nucleus is what? Extremely small. You don't have to put a number. I mean, I asked for the number in class. Okay, during lecture, I actually asked the whole class, do you have a number in mind as far as how big the nucleus is relative to how big an atom is? And I think we have a pretty good idea. I remember that particular lecture when we talk about the structure of the atom. So this is extremely small. This is actually quite large. Okay, so that's it. The 2x2 table is complete. Okay, the mass of both the nucleus and the atom are the same, but the nucleus is extremely small and the atom is relatively large. Okay, so I asked a follow-up question just to make sure you know what's going on. I asked another follow-up question. Okay, which is, in other words, is the density of the atomic nucleus higher than, equal to, or lower than the density of the overall atom? So I asked you, okay, the density, right? Which one is bigger? Okay, should they be also the same, like in a previous case for the mass? Or should the density of one being greater than the other? And explain briefly. Okay, so which one has a higher density? The nucleus or the atom? Yeah, it has to be the nucleus, right? Okay, same mass, but one has a tiny little volume, so it's very dense. The other one has, yeah, the same mass, but over a large volume. Okay, so this is going to be denser, right? More dense. This has to be more dense than the atom itself. Okay. So I actually asked for an explanation, but this table is the perfect explanation. So it depends on how you answer the question. Okay, if you just kind of compare things like the way that I suggested, then there's no need for an explanation. Because clearly, density is mass per unit volume. And we talked about this during one of the earlier tutorials. Okay, just how much mass or how much amount. I mean, it does not have to be mass. Okay, density is usually defined to be something per unit volume, and that something does not even have to be mass. It could be mole, right? You can count how much of something you have within a certain volume. So it's moles per volume. This is known as what? Do you remember from your lab? This is known as the molarity. This is the molarity of something. Okay, it's not density, but it's kind of like density. But this is called molarity. Okay, this is called density. And you can also have number density, which is the number of something. Number of whatever it is per unit volume. Okay, so as long as you understand that density is given by mass over volume, and you can compare the density of the nucleus against the density of the atom. Okay, that's all I'm asking for this question. It's a 6-point question, so if you give a reasonable explanation, then you pick up all 6 points. But if you're missing something in your explanation, then you may have fewer points. Part B of the same problem asks you to calculate something. Okay, the density of cobalt, the element cobalt, is 8.9 grams per centimeter cubed. Okay, so this is given. This is the density of cobalt. Okay, in a 1 cubic centimeter sample. Okay, so you're given a sample of 1 cubic centimeter size. Okay, and this is given. How many atoms of cobalt are there? That's it. That's the question. Okay, you're given this size of cobalt. How many atoms of cobalt? Well, this is the volume given, which is not a big volume. 1 centimeter cube is just that tiny little, volume. But in 1 centimeter cube, I know I have 8.9 grams of cobalt, because that's what the density tells you. So we have 8.9 grams of this element, cobalt. Okay? So how do I know how many atoms of cobalt there are in 8.9 grams of cobalt? So I gave you a hint. Right? In answering the question, you need to look up the molar mass of cobalt from the periodic table of the elements. Okay? So I go ahead and look that up. Cobalt looks like it's about what? What is the atomic mass of cobalt? And I'm sorry, I'm a little unprepared today because I should have brought a book and I should have brought a calculator. Can you help me out here? What is the atomic mass of cobalt?
59.
Okay, about 59. Okay, 59 grams per mole. Right. So do I have a mole of cobalt? Because if that's the case, then you don't have another step in the calculation. Because if you have exactly 59 grams of cobalt, that tells you that you have 1 mole of cobalt, right? Mole is what? Mole is a number. Okay, mole equals to 6.022 times 10 to the 23rd. Okay, so if you have a mole of cobalt, then this is the number of atoms of cobalt you would have. Okay, but you don't have a mole. You have, only 9 grams, not 60 or 59. Okay, so what is the ratio here? 9 divided by 59. So how many moles of cobalt are you looking at? Definitely less than 1. Okay, because it takes 60 grams to make a mole. So you have less than 10. So 10 is less than 60. So what is this number here? Again, I don't have a calculator. Can you help me calculate this? Just take 8.9 divided by 59.
0.15.
Okay, 0.15. Okay, that's about right. Moles. Okay? So you have about 0.15 moles of cobalt. Okay, how many atoms? Well, you're going to have fewer than 6.022 times 10 to the 23rd. Right? So let's take 0.15 mole, okay, multiplied by 6.022 times 10 to the 23rd atoms per mole, right? That's what the mole represents, okay? So it's 0.15 mole times 6.022 times 10 to the 23rd atoms per mole, okay? So the per mole cancel. So what is 0.15 times 6.022?
2.50.
2.50 2.50 times 10 to the what power?
Negative 25.
Negative? Well, multiply. These two should multiply. Because the power should be quite large. May not be as large as 10 to the 23rd power, but it should be still quite large.
9.03.
9 point, 9.0.
9.03 times 10 to the 22nd.
Okay. The rest of you, do you agree? Okay. Well, just take 6 times about 0.15, 0.2. So 20% of 6, that's, well, actually no, 15% of 6. So yeah, about 9, that's right. Okay. So I think this makes sense because, what is 9 times 10 to the 22nd atoms? Well, 9 is about 10, right? 10 times 10 to the 22nd, which is 10 to the 23rd. So, even though you don't have exactly a mole of atoms, okay, but you have, pretty much just like a mole of atoms, okay? Because even though you only have 10 grams, which is less than the 60, but, in the bigger scheme of things, you still have roughly a mole of atoms, right? Because 9 is about 10, right? You can round it up to 10, so 10 times 10 to the 22nd is 10 to the 23rd, which has the same order of magnitude as the Avogadro's number. Okay, you have, if you really want to answer the question, then you should have just said, okay, you have about 1 mole of cobalt atoms. But if you want to actually do the calculation, you should have answered 9 times 10 to the 22nd number of cobalt atoms. Okay? Or some of you might have learned how to do this in high school. And you go ahead and set up the calculation like this, which is okay. And I'm going to show you what it looks like. Okay, so you're going to start with 8.9. I'm sorry, you're going to start with the 1 centimeter cube. Right? You start with the 1 centimeter cube of cobalt. And then you go through what we call dimensional analysis. You just keep changing the units. And we talked about this during the first tutorial, right? If you want to change the unit, just keep multiplying by the proper conversion factors. I know, okay, for cobalt, it's 8.9 grams of cobalt per centimeter cube of cobalt. This is called the density of cobalt. It's given to you, okay? So let's make use of it, okay? Cancel the centimeter cube of cobalt. Now I have grams of cobalt, okay? How do I convert to some other units, okay? So apparently you need to use the molar mass. Because otherwise, I don't know, in 8.9 grams of cobalt, how many moles. So I gotta use the 59 grams. Okay, the 59 grams of cobalt per mole of cobalt. Okay, so the grams would cancel. Okay, and now we have moles of cobalt. And I know 1 mole of cobalt is 6.022 times 10 to the 23rd, that many atoms of cobalt. I think that's how students are taught in high school how to do this. Okay, so I would prefer that you think about what's going on. Okay, instead of just line up the numbers. Okay, because it will give you a sense of where you're going, right? You have a centimeter cube of cobalt. So it's 8.9 grams, okay? And in 8.9 grams, you have, obviously less than a mole of cobalt. But to be precise, that's about 0.15. And once you know how many moles of cobalt you have, you can just figure out how many atoms by multiplying. This is the only step that really require the use of a conversion factor, which is this one, the Avogadro's number. Okay? But anyways, you should have the same exact answer, 9.0 times 10 to the 22nd atoms of cobalt. Okay, so this is what I'm expecting from part B. It's a 4-point calculation. So obviously, partial credits will be given depending on how far you've gotten. Okay, but if you have the final answer and it is correct, then you'll get the 4 points. Whether you do it like the way I showed it to you first, or you do it like the high school chemistry way, which is also probably what the textbook showed you in this class, okay? Or the textbook for this class showed you. So part A, part B of problem 2. Any question on this? Okay. Problem 3 is hopefully very straightforward for many of you. So problem 3 look like this. According to this version of the exam I'm looking at, answer all of the following questions regarding the hydrogen atom. So I guess, some of you like to read questions carefully, others kind of skip over important information. So all I'm asking you to think about is the hydrogen atom, okay? That's it. Okay, don't think about the helium or lithium or any other elements, just the hydrogen atom. And answer the following questions. And ask you 4 questions. Question A, part A, asks you to sketch the Bohr model of the hydrogen atom. Okay? So here's what I expect. Okay, you need to give me the nucleus of the atom. So I ask you to label the nucleus. Okay? So just put a dot or draw a circle, whatever you want to represent the nucleus. Okay, it doesn't really matter. And label at least the n equals to 1, n equals to 2, and n equals to 3 orbits. Okay, so Bohr's model, which is very simple and yet very powerful, look like this. Okay, you would just have these circles, okay, surrounding the nucleus. Okay, and you can draw as many circles as you want, but all I ask for are the first 3. Okay, just to stop you from, keep drawing more and more circles. And you should label these circles n equals to 1, n equals to 2, and n equals to 3. Okay, that's all I'm asking. The Bohr's model look like this. Of course, there are implications about, where to find the electron. So hydrogen has only 1 electron, right, because it has 1 proton. So Bohr actually assumed that the electron is just going to orbit the nucleus like a planet orbits the sun. Okay, you think of the sun, right? And then you have these planets orbiting the sun. It's kind of what Bohr has in mind for the hydrogen atom. Okay, which is a very powerful model, nevertheless, because it explains a lot of observations that that people before Bohr couldn't explain. Okay, using other models of the hydrogen atom. Okay, so that's why I'm asking for Bohr's model of the hydrogen atom. It's 4 points. Okay, part B. Okay, so now I'm stepping up the level of difficulty. Okay, this is a very simple model. Okay, but here comes Heisenberg uncertainty principle, HUP. Heisenberg uncertainty principle. Okay, I ask you what does it say? Okay, what is the meaning of the Heisenberg uncertainty principle? Okay, well, there is a mathematical way to express this, which is delta x times delta p greater than equals to h bar over 2 pi. This is the mathematical way. What this is saying is that we cannot determine the exact position of these very small objects, such as an electron, okay, without introducing incredible error in the conjugate variable. I mean, position is x, momentum is p, and they're conjugate. In classical physics, in Newtonian mechanics, right? All of you know classical physics, right? Okay, you know Newton. You know what he said, right? Well, Newton said you should be able to determine both at the same time, the position and the momentum or velocity, whatever you prefer to think of it. So it's position and velocity. It's like this eraser. Okay, I'm just going to leave it here. Do you know where to find it? Yes, right? Do you know whether it's moving or not? Yes, you do, right? Because it's not moving, it's at rest. Which means that tomorrow you come back, it will still be here. Okay? 2 days later, 5 days later, a month later, you come back, it will still be here. Unless what? Unless it's moved. Unless someone give it a little push and move it. Otherwise, for an object which is at rest, it will always be at rest. And and according to Newton, we should be able to determine positions of any object. Okay, this principle is going against classical physics. Okay, because it is saying that, well, these electrons, right, because they're so small and so, I guess, they're just not the kinds of things that you would compare to something as big as an eraser, then electron is almost nothing, right? It has almost no mass. It barely has a charge, but it's what makes the particle an electron, because it has actually a charge. So the Heisenberg uncertainty principle basically said that for an electron or for a photon, okay, for these very tiny little particles, so for electrons or for photons, okay, it is impossible to determine position and momentum at the same time. And momentum at the same time. Okay, which implies what? Well, if you're not going to determine the position of the electron, that means Bohr's model is wrong. Because Bohr's model said that, well, you should be able to find the electron on the orbit. Okay, so this is basically what? Throwing away Bohr's model. And also introduce the idea that the probabilistic view of nature makes sense. And I think I mentioned this in class, in lecture. Einstein has a lot of trouble accepting this. Okay, being a good physicist, I mean, he came from the tradition of classical physics, right? So how can he just all of a sudden abandon? I mean, it's almost like you live on this planet for so many years, and all of a sudden you have to abandon everything you knew about your existence on this planet. You have to accept a new set of values, a new set of standards. That's crazy, right? But unfortunately, well, that's what is real. Okay, that the probabilistic view of nature makes sense. So I'm not going to even bother to find the electron. I'm just going to say, well, okay, yeah, I know the electron has to be close to the nucleus. Otherwise, we don't have atoms. All I'm interested in is the probability of finding the most number of electrons. Okay, so that's what the quantum model looks like for the atom. So part C, I actually asked you for the quantum model. Okay, I didn't say it, but it is the quantum model. Okay, well, not only that, I'm interested in the probability of finding the electron, but the probability correlates with energy. Okay, because yes, let's say the two orbitals, right, 1s and 2s. So these names. There are two different orbitals. One is called 1s, the other is called 2s. Okay. Well, what does that tell you about the electrons found in this versus this orbital? Okay. Well, look at the first number. Okay, in these various names, the first number is actually the n quantum number, right? Which is the same as what you use to label these orbits. Okay, so this 1s orbital, right, actually represent, like a spherical shape, which describes what we call a probability density, a probability, contour. Okay, so it's going to be almost have to redraw the picture. You have the nucleus, right, and then now you have the, this region in space, which looks like a spherical shape. Within this region, okay, I know I have a good probability of finding these 1s electrons, so so-called 1s electrons. And the 2s orbital, right, it has the same shape, okay, because the s, the lowercase s, tells you the shape of the orbital. So it has the same shape, but it's 2. N equals to 2, so it should be a little bigger, right? So why is that the 2s electrons should have more energy than the 1s electrons? Well, because the 2s electrons are being found at a distance a little farther away from the nucleus than the 1s electrons. Okay, so the quantization idea, why is it quantum? Well, that's because these electrons, if you compare 1s to a 2s electron, they do have different amounts of energy. Okay, this has energy E1, this has energy E2. And they're very specific. Okay, so these so-called discrete energies is what makes it quantized. Okay, because it's discrete. That's why it's quantized. Versus what? Versus in the case of classical physics, everything is continuous. You know, if I push this eraser, you can see it, right, going from here to there. And it's not like, okay, this eraser that starts here, it's just going to jump, 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 jump like this. Right? You can actually see continuous motions. But in quantum mechanics, you don't see that. You see, you know, it goes from E1 to E2. Okay, I mean, later on, you're going to do an experiment, which is called spectroscopy. And during that experiment, you'll get a chance to ask these questions again. You know, regarding what's the difference between quantum and classical physics. But anyways, part C asks you for the number of atomic orbitals in each of these energy levels. So you have n equals to 1, n equals to 2. I mean, these are the same as the Bohr's energies, except, of course, you don't have the orbits under the quantum model. These are just, you know, labels that we use to label the atomic orbitals. Okay? So these are orbits. We have to throw them away because they are not accurate descriptions of atoms. Okay? So we have these orbitals instead of the orbits. And we know these orbitals are, you know, found in each of these energy levels. So I asked for the set of quantum numbers that will give you the orbitals in each of these levels. So the idea is you're going to use NLM, right? So the first digit always stands for the n quantum number. L is always the second digit, and M is always the third digit. See you later. Okay, so the rules of quantum mechanics specify that there are restrictions to, you know, these NLM quantum numbers. And I know this is not something that's going to make a whole lot of sense, okay? But what I'm trying to do is to give you the basic facts, but I also teach you how to use them so that it will make some sense to you. It's not going to make complete sense because this whole idea of quantum mechanics does not even make sense to Einstein. I mean, how can you all of a sudden say that it makes sense to you? But you know, we have to accept the fact that this is what the experiments that you know, a lot of people had done had informed us. Okay, so these are the rules on the quantum numbers, and if we play by the rules, then maybe things will kind of make some sense. Because in the second energy level, right, in the n equals to 2 level, okay, the quantum numbers are more, right? You have 2, 1, 0, 2, 1, minus 1, 2, 1, 1, okay? Which explain why, okay, in the first energy level, there's only one orbital. In the n equals to 2 energy level, there are now 4, because you have 1, 2, 3, 4, you have 4. In the n equals to 3 energy level, you have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so you have altogether 9 different orbitals, which follows the formula n squared, and I give that to you as a hint on the exam, right? So n equals to 1, 1 squared is still 1, so there's only one atomic orbital under the first energy level. Under the second energy level, you have n squared, which is, you know, 2 squared, which is 4. So you have 4 orbitals, 1, 2, 3, 4, they're all here. And for n equals to 3, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. You have n squared, which is 3 squared, which is 9 total atomic orbitals. Okay, so that's basically what I'm asking in part C, just to count the number of atomic orbitals. But you know, there are a lot of things that I cannot possibly ask on an exam. But I hope you understand, because you know, obviously, knowing the quantum numbers would help, but it's not the whole, the whole picture. And knowing these numbers would help, but eventually you would have to try to understand better. And then let me just quickly go through part D, and then for those of you who need to go, of course you're free to go. So, and I'll continue to go over the rest of the exam, but it's going to be on tape, so you don't have to feel obligated to stay. So part D, let me just quickly go over this. Part D asks you to use your knowledge of the set of quantum numbers n, L, and M. Okay, prove that the H orbital would have 11 H orbitals. Okay, you see there are 3 P orbitals. These are the P orbitals, 1, 2, 3. And these are the D orbitals, 1, 2, 3, 4. But this is wrong. This is not it. So it's 1, 2, 3, 4, 5. So, the S orbitals has only 1. P has 3. D has 5. Okay, F has 7. So you've seen all these already. The next one is G, and then the next one is H. So for the H orbitals, how come there are 11 of them? And you're supposed to prove this using the set of quantum numbers n, L, and M. Okay, I gave you a hint on this problem, which is to use L equals to 5 to represent the H orbital. Because this is L equals to 0, to 1, to 2, 3, 4. So use L equals to 5 to represent the H orbital. Now, the only thing that you should worry about is the next quantum number, because the n quantum number does not tell you the number of orbitals. Only the m quantum number, the magnetic quantum number, tells you that. Now, the magnetic quantum number is always restricted from minus L to positive L, which means that, okay, if L equals to 5, then the magnetic quantum number is restricted to all these integers, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5. So let's count. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that's why you have 11 H orbitals, because there are 11 possible magnetic quantum numbers, okay, that can be generated by L equals to 5. Okay, so like I said, this is probably a little trick that 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 looks impressive, but it's not the whole quantum model. Okay, there are many little things about a quantum model that you can learn about, read about, and try to understand more about. Okay, but this is kind of the minimum I would expect from you to be able to do. Okay, at this level. Okay, any question? Yes.
I want to ask one quick question about the orbitals. I think it was or C.
C. Okay. Right here.
Is that the same? The subshells are not part of the. Are they considered in the orbital? I mean, are they part?
Well, this is called subshell because this is a shell. The n equals to 1, n equals to 2. That's labeled as a shell. So in the n equals to 2 shell, there are 2 subshells. The S subshell and the P subshell. Is that what you're trying to clarify?
Yeah, I think it was.
So here you have a subshell. Here's another one. Here is another one. So it's just depending on how you want to think about organizing the information. And I think in the book it says that this is how you can organize the information, right? 1, 0, 0, 2, 0, 0, 2, 1, minus 1, 0, 1. You're drawing trees instead of making a list of these levels. So this is the energy level, and these are the sub-levels. So the level right below the main level is the sub-level. Okay? Other questions? Okay, if you have to go, just go, okay? I'm just gonna since I'm taping myself, I'm just going to go over the next 4 problems really quickly. Okay, but if you want to stay and listen, of course you're more than welcome to do so. Okay, so going on to problem 4. Okay, again, this is version 1 of the exam. So we talked about 1, 2, 3. This is problem 4. Problem 4 is actually very simple. It says, explain briefly how one determines the shape of an atomic orbital knowing psi, where psi is the normalized wave function of a hydrogen electron. So, I introduced this symbol in class, and I gave it several different meanings. One is called atomic orbital, okay, and it is also called a wave function. Okay, why is it a wave function? Well, because we're going to use this to represent electrons, and the wave particle duality informs us that an electron can behave like both wave and particle. So it makes sense for us to use a wave description of an electron, as well as the particle property of electron to describe, the nature of electrons, as they, as they're being found outside the nucleus of an atom. So, so this is once again mentioned in problem 4, but you're being asked to explain how we can use this symbol, or how to use this, use the information contained within the wave function in order to determine the shape of these different orbitals. So this already represents the orbital, right? How can we determine the shape of an orbital? Okay, well, this is what I expect. Instead of me drawing the integral for you, you are going to give me the integral. Okay, and that's it. If you can just put down the integral. Just like when I asked you for the Heisenberg uncertainty principle, right? You could have just put down a mathematical equation and say, well, this is it. That's why mathematics is quite powerful in the physical science, at least, because one mathematical equation means a whole lot. Okay, so to answer problem 4, basically all you need to do is to show me this integral. But of course, if you don't feel very comfortable with the mathematics, you better attach a little verbal or textual explanation. So here what you want to do is, so yes, we have this wave function, right? We have this atomic orbital. What we are going to do is we are going to, first of all, understand that the atomic orbital is psi, right? But we need the psi squared because it will actually give us probability density. Okay, well, why do I call it probability density instead of probability? Because, psi squared tells you okay, if you go from the nucleus and out, okay? So let's say this is the atomic nucleus, and you're going outside the nucleus and try to find the electrons, okay? The probability density is basically some sort of probability distribution, okay? So unless you do integration, you know, unless you actually say, okay, I'm going to find out all the probability, okay? If I go this far out, you know, R equals to whatever. If I go this far out of the nucleus, what is the total probability of finding some electrons? Okay, so that's why you need to integrate, because integration means, you know, summing up all the probability. Otherwise, you only have the density. You don't have the total probability, right? But why do we care about the total probability? Well, because that's going to inform us the shape, right? I want to know, I want to be able to ask this question, okay, which is, I want to find out the shape of that region, okay, in 3 dimensions. So that's why it's dy, dx, and dz. I want to find out, okay, the region in space outside of the nucleus in all 3 dimensions. That would guarantee at least this probability of finding electrons, okay? And you can even be more specific. You know, if I'm looking for the 1s electrons, then I would have to integrate this wave function. If I'm looking for the 2s electrons, I'm going to have to integrate this function. And if I want to look for the 3s electron, I would have to integrate this function. So you're doing, you know, each integral for each of the orbitals, okay? And that's how to figure out all these shapes, you know, spherical shape, or in the case of, you know, the p orbitals, right? Something like 211 or 210. Okay, because the L quantum number tells you the shape of the orbit. Well, it tells you what sublevel you're in. I mean, you're right. This tells you what sublevel you're in. But as you integrate, right, it will tell you, okay, well, this wave function, once you integrate, actually this one, the one with the square, will tell you. I mean, it will tell you the shape, okay, of the space, you know, outside the nucleus. That would give you the highest probability. I mean, they will give you a collective 90% probability of finding, you know, these electrons that you were looking for. Okay, so this is a very powerful equation, actually, if you think about it. Okay, this is how we come to an understanding of the shapes of the different orbitals, whether it is S, P, E, or F. You need to go, or? You have a question?
I was saying that as you explained from before, much
Yeah.
that's different.
Okay. Well, thanks for staying. Have a nice break. Okay, so number 5 is a little different, because once we have these atomic orbitals, then we can do something like expressing the electron configuration of the other elements. I mean, the other elements other than hydrogen. Okay, because we know a great deal about hydrogen. Okay, because it is simple. It has only 1 proton, 1 electron. But the rest of the elements on the periodic table, they have, more than 2 electrons, 2 or more electrons. So they're not as simple as the hydrogen, but we come up with this idea that, since we know the hydrogen orbitals, why don't we just pretend that the other elements are simply, using these orbitals for holding, more than 1 electron. So that comes the idea of electron configuration, which is problem 5A at least. Okay, so 5A is asking, okay, what is the electron configuration of lithium? Okay, so I give you an element, which is lithium, and and I asked you for the electron configuration. Part A also has several other elements. So you have lithium, neon, phosphorus, P, and arsenic, AS. Okay, so you've got 4 different elements, and they are both, they are all so-called multi-electron elements. They all have more than 1 electron. Lithium has 3. Okay, neon has how many? I think 10, right?
Yeah.
Okay, phosphorus has how many?
15.
15, okay, that's good. And arsenic has 33, I think.
Yes.
Okay, so obviously these are all elements with more than 1 electron. And the idea is, okay, well, we're going to use something like the hydrogen orbitals, okay, and just fit the 3 electrons in these various hydrogen orbitals, okay? And that's why we come up with this idea that we're just going to, instead of putting the 1 electron in 1s like in hydrogen, we're going to fit 2 electrons in the 1s orbital, and we'll fit 1 electron in the 2s orbital for lithium. And this is the correct electron configuration for lithium. For neon, okay, we have 1s2, 2s2, and 2p6. Okay? And for phosphorus, we have 1s2, 2s2, 2p6, 3s2, 3p6. So this is, well, actually there are too many electrons already. So it's 2, 4, 6, that's 10, 12, 15. Okay, 3p3. And for arsenic, it's 1s2, 2s2, 2p6, 3s2, 3p6. That's 18. Okay, the next orbital to fill is actually 4s, so it's 4s2, and we are at 20. Okay, the next orbital to fill is the 3ds, and we can fit 10 in 3d orbitals. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and after 3d is 4p. And actually, we don't fill the 4p orbitals. So we only put 3 electrons in the 4p orbitals. And in fact, what happens is, let's see, if you follow the order of filling the orbitals, P, 5P, 3D, 4D, 5D, etc., right? So you go according to this order. Okay? So you go from 1s to 2s to 2p to 3s to 3p, 4s, 3d, 4p. So you basically have electrons filling everything up to the 3d level. Okay? So actually, even if you switch the order of these two, okay, so if you have 3s2, 3p6, 3d10, 4s2, 4p3, this is not wrong, okay? Because everything is filled, right? This is filled, this is filled, this is filled. This is the first energy level, second, and third, right? First energy level can hold 2 electrons. Second one can hold 8. Third one can hold 18. So all these are filled, okay? So as long as you demonstrate on the exam that these orbitals are all filled, okay? I guess, if you want to put them in a nice order, that would be great, but most importantly, the 4th level, which can hold a maximum of 32 electrons, is not filled, right? Because you only have 5 electrons in the 4th energy level, okay, for arsenic. And later on, we're going to look at, the meaning of valence electrons, and that's essentially what we're going to be looking at, to compare, the shells that are filled and the shells that are unfilled. So we'll, figure out, okay, the chemistry of these various atoms of different elements are all basically given by the number of electrons in the valence shell of an element. It's an extremely critical idea, really, because, I mean, unless there's a new model, otherwise, you know, we've been using this model for a long time, and I mean, relatively speaking, a long time, and the model still works. So we're going to talk about the chemistry of valence electrons after spring break. But so problem 5 actually has a part B. Part A is just to ask you for the electron configurations. Part B is to basically, well, part B has a question that is aimed at probing whether you know why you can put 2 electrons in the same orbital. So like, you know, how come 1s can put 2 electrons, 2s you can put 2 electrons? Or each of the 2p is actually there are 3 2p orbitals, 2px, 2py, and 2pz, but each one can hold 2 electrons. So that's why altogether the 2p orbitals can hold a total of 6 electrons. So for what reason that 2 electrons can be found in the same orbital simultaneously? And the answer is spin. Okay, spin is the reason why you can put 2 electrons in the same orbital. I mean, in every case, it's the same answer. Okay, why do I put 2 electrons in 1s? Because, you know, they have different spins. How come I can put 2 electrons in a 2px orbital? Again, because they have different spins. So it's not possible to put a third spin, to put a third electron in an orbital. Okay, not possible for third electron in an orbital. Okay, because, you know, there are only 2 spin states, you know, plus 1/2, minus 1/2. Okay, so if you put a third electron in the same orbital, it would have either a plus 1/2 or minus 1/2 spin state, which means that you're repeating one of the spin states, and that's a violation of the Pauli exclusion principle.
What about an example of boron?
In boron, what about boron?
Like the configuration
Okay.
of 5.
So let's look at boron. So boron has 1s2, 2s2, 2p1. Right, so what about boron?
So in the first orbital it has 2, in the second one it's holding 3.
No, the second one, which is 2s, can hold only 2.
Okay, so that's considered.
The last one goes in a different orbital.
Okay.
So it's not, yeah, it's not like the 1s can hold 2, and then you have one that can hold 3. No, it's not like that. It's, the next one is also holding only 2, so you need another one which holds only one of the boron electrons. Okay, so that's 5b. Okay, 6 and 7 are both stoichiometry calculations, so which is very different from the quantum questions we've been focusing on. Okay, so let's go over 6 and 7, okay, even though they are very different problems. Okay, so you've done so much on quantum. Okay, well, we need to kind of take a step back and now, you know, look at some of these chemical reactions that you've been learning since the beginning of the semester, like this one on problem 6 of version 1 of the exam. It says freons at one time were used extensively in spray cans and as coolants in refrigerators and conditioners. Unfortunately, they contribute to global warming and attack the Earth's protective ozone layer. one of the most promising substitutes is C2H2F4. So we're not going to use the freons anymore. We're going to use C2H2F4. Okay, C2H2F4. That's called HFC 134A. Which HFC 134A, which you might be familiar with. This training this compound C2H2F4. It's also known as HFC 134A. HFC-134A. The chemical reaction I gave you is actually this one. C2H3 liquid reacts with HF gas to form C2H2F4 liquid. So this is how you make the HFC-134A liquid product. Okay, so by reacting this compound with HF gas, you're going to make the HFC-134A. Okay, so in a particular experiment, you have 100 grams of this, and you have 30.12 grams of this. So you have two different amounts for two different reactants. The actual yield of the product was 95.2 grams. Okay, and of course, I don't know which one is the limiting reactant. So you have to first of all ask yourself this question: is this limiting, or is this limiting? Okay, because when you add these two numbers, right, 100 grams plus 30 grams, you don't get 95. You have 130. So actually one of these. Well, the whole idea of limiting reactant is that, okay, one of the two reactants will be consumed completely. Okay, so that means what? Well, that means maybe only a fraction of this 100 grams is being used, while all of this 30 grams is being used. Okay, or you use up 100 grams of all of this, and you use up all 100 grams of the first reactant, but then you don't use up all of the HF. Okay, and you're gonna make your product, and the question also said that there are some byproducts that are generated. I guess all I'm saying is you can't just add the 100 to 30 and assume that all of the reactants will be used, okay, to produce whatever product. I mean, this is called the actual yield, which we're going to need later for the percent yield calculation. Okay, but for now we should just ignore it. We don't know, okay? We don't know theoretically which one is the limiting reactant, which is basically the first question for part A. This is part A of problem 6. Okay? So what I need to do is to think about what's going on. And you have 100 grams, 30 grams. Okay? And then you have 100 grams of the C2H3, and you have 30 grams of HF. Okay? Just two different reactants, two different amounts, and we need to consider them separately. Okay? And there are several ways you can answer this question. First of all, I'm going to do it one way, okay, and I'll just describe orally what are some other ways of answering this question. So the first way is I'm going to pretend that I have 100 grams of C2H3, the first reactant, ignoring the presence of HF, and assume that I have a lot of HF. So I'm just going to focus on using up the 100 grams of C2H3. Okay, now to figure out how much product I'll produce by using up all of the 100 grams of C2H3, I need to do the three-step process. Right? This is the calculation of theoretical yield kind of calculation. Okay, so theoretically, if I use up 100 grams of this reactant, ignoring the presence of the other whether I have enough or not. Okay, right now, I assume it doesn't matter to me. So all I care about is to apply the three-step process in order to figure out the theoretical yield if I use up 100 grams of C2HF3. So I'm going to do what? I'm going to, the first step is to convert from grams to mole. So I'm going to need to figure out the molar mass of C2HF3. Okay, and unfortunately, I don't have a periodic table. So can you help me out here? Just take 2 times 12 plus 1. And fluorine is how much mass per fluorine?
9. Oh, sorry, 18.
18? About
19.
18, okay. So 3 times 18. So it's 2 times 12 plus 1 plus 3 times 18. What's the total mass? So this is 24, this is 1, 18 times 3 is 54, something like that. Yeah. So it's 54 plus 24 plus 1, so that's 79 altogether. Okay, so 79 grams per mole. So I know that if I have 79 grams of C2HF3, this is 1 mole of C2HF3. Okay, and so the first step is just to convert from grams to mole. Well, why do I want to do that? Because I'm going to use the mole ratio for the next step, okay? And in fact, I should have checked the chemical equation to make sure it is balanced, okay? And I checked, and actually it is already balanced. This is 1 to 1 to 1, okay? These are the ratios. So that makes this calculation a little simpler, because the number of moles of the reactant, C2HF3, is, 1 mole of that reactant is going to produce 1 mole of the product, C2H2F4, okay? So now all I need to do is to figure out also the molar mass of C2H2F4. So C2 is 2 times 12, H2 is 2, F4 is 4 times 18. So that's 24 plus 2, 18 times 4. So add 18 to 54, which is 72. Yeah, okay. So it's altogether 98. So it's 98 grams of C2HF3 per mole of C2HF3. Okay? So this is a 3-step calculation. The most important step, I think, is the middle step, relating moles of one to moles of another in the balanced chemical equation. Okay? The first step is just to convert from grams to mole. And then the last step is to convert from moles back to grams. So what is the answer here? You take 100 times 98 divided by 79, what do you get? So 980 divided by 79.
Divided by 24.
Okay, 124 grams. Yeah, let's just take 124, okay? This is the amount of product, the HFC 134A compound, okay? We're going to make 124 grams of this compound. If you react entirely to 100 grams of the first reactant, which is C2HF3, right? Okay, that's just half of the calculation. The other half of the calculation is you have to kind of ignore everything that you've done so far and just pretend that 30.2 grams of HF is all you've got. And you got to react all of it away, pretending that you have a lot of the other reactant. Okay, so you're doing the same set of calculations, except that you have to switch your assumption. In this case, you're going to assume that you'll use up all of the 30.2 grams of HF. And you have unlimited supply of the other reactant, C2HF3. Okay, so HF is a little simpler as far as the molar mass is. F is 18, so this is 19 grams of HF per mole. So you're going to, do the same 3 steps, right? And then this is mole of HF to mole of C2H2F4, and then the last one is still 98 grams of C2HF3 per mole of C2HF3. Okay? Okay, so now you need to help me again. Take 30.2, multiply by 98, divided by 19. 155.76. 78. So let's just make it 8. 155.8 grams of the product. Okay, so you have two different amounts of the product, right? Which one is the correct amount?
What was that?
Okay, you have two different amounts. Which one is correct? You have two different answers. One of them is correct, the other is not. Which one?
This is the one that I said.
Right, the first one is correct. Why? Because the limiting reactant will always give you less amount of the product. Okay, the limiting reactant will always give you less amount of the product. So, in fact, in this case, the C2HF3 is the limiting reactant. You're going to use it all up. You're going to use up the whole 100 grams of C2HF3. Okay, and you have some left over. Really, you have some left over of HF. So you're not going to use up the whole 30.12 grams of HF. You're only going to use up 100 grams of C2F3, and you can actually calculate using a very similar process. Okay, if you react 100 grams of C2HF3, how many grams of HF do you need to have at least? What's the minimum amount of HF that would react with 100 grams of C2HF3? You can calculate that, but I'll leave it up to you if you want to figure that out. But here, as far as finishing up the problem, 124 grams is the theoretical yield. Okay. Part B asks you to calculate the percent yield. So once you have the theoretical yield and you have the actual yield, you can calculate the percent yield. So just a very tiny additional step of calculation. So 95.2 divided by 124 multiplied by 100. So taking the actual yield divided by the theoretical and multiplied by 100. So what is this? 95.2 divided by 124 times 100.
76.7.
Okay, that's the percent yield. 76.7% is the percent yield. About 80% yield. Okay, so this is one of the two stoichiometry problems. The other one.
Is there any particular reason you decided to start with the 100 grams?
No, I could have started with the 30.2 grams. I mean, the order of these two calculations can be reversed, but the nature of these calculations cannot be changed because this is precisely the way that we can tell which one is the limiting reactant. I mean, you cannot start with any other number. I don't know. There's nothing you can do with 95.2. This number should have been ignored altogether. Yeah, so you have to. Well, you can start with 30.2 HF, and then you calculate. Okay, if you use up all 30.2 grams of HF, you would have produced about 160. 156 actually, 156 grams of the product, right? So if you do this calculation, then you're going to realize, well, this is not complete. The information here is not complete because I still need to compare this number, 156 grams, to the other number, which I can only obtain by taking 100 grams of the other reactant and figuring out what is the theoretical yield if I use up all 100 grams of that reactant.
And you found out that the top one was the right answer because
It's smaller.
because it's
Yeah, the limiting reactant always give you less product.
Okay.
Okay? I mean, it's like what I try to explain in lecture. You know, when you're cooking, right? You have I don't know. You know, let's say you make salmon for dinner, and you know you got your piece of salmon, and you got. I mean, let's say you have 2 pieces of salmon, of salmon steak or some kind, and you have other ingredients, right? You know, lemon and butter and whatever. Okay, what determines how many dishes you can make? Well, the number of salmon steaks. You know, you only have 2 pieces. That dictates how many dishes of salmon dinner you can make, right? Whether you have a lot of butter doesn't matter. Whether you have a lot of you know, lemons and other ingredients doesn't matter. As long as you only have 2 salmon steaks, you're going to make only 2 dinners. So the limiting reactant will always give you the least amount of product, and that's what you have to do. You can figure out how much product you're going to make per reactant if you use it all up, and whichever amount of product that's the smallest is going to give you an indication of the limiting reactant. So doing exactly what I just did would be the best way to tell. Okay, I mean, I've seen students doing things in a very strange way. Like, you know, I don't even know how to describe what they're trying to do, but, you know, they just decided to go about doing this in a very different way. And unfortunately, in this particular scenario, okay, doing it in a different way is not going to work. You have to just follow the steps and understand what is limiting reactant and be able to follow through the calculations, you know, determining the proper product use and compare, you know, the numbers, and whichever number is smallest, that's going to indicate the limiting reactant. Okay, so the last problem is problem 7. Okay, and it says, recall from the previous exam that nitroglycerin, which has this formula C3H5O9, N3O9. Okay, this is nitroglycerin. So recall from the previous exam that nitroglycerin is a powerful explosive. Once again, the following chemical equation may help explain why. So I'll give you the exact same chemical equation from the previous exam. So it's N2 plus CO2 plus H2O plus O2. So I give you a bunch of these product gases, and then it says, you know, part A obviously balance the chemical equation. Okay, so I suggest using the coefficient of 1/2 in front of O2. Okay, because it makes balancing a lot easier. So what I'll do is, you know, if I have 1/2 O2 on the right, okay, in fact, you know, let's just go through the whole process. Okay, we've got carbon, hydrogen, nitrogen, and oxygen. We've got 4 different elements in this reaction. On the left-hand side, I've got 3 carbon. Right-hand side, I've got just 1. Left-hand side nitrogen, I have 3. Okay, right-hand side nitrogen, I have only 2. Left-hand side hydrogen, I have 5. Right-hand side, I've got 2. Left-hand side oxygen, I've got 9. And right-hand side, I've got, this is 1. 1/2 of O2 is 1. Plus 2 here, plus 1 here, I have 4. So,
1/2 of O2.
yeah, O2 has 2 oxygen, right?
Okay.
So, you know, just half a mole of that means, you know, just 1. I mean, it's not like you're breaking the bond between the O2. You just don't have as many O2 molecules. It's 1/2 mole. So, I mean, 1/2 of O2, just pretend this is 1 oxygen. So it's one 2, so altogether 4 oxygens. And of course, by looking at the numbers of atoms of different elements, okay, the equation is not balanced. So we got to balance carbon, nitrogen, hydrogen, and oxygen. Okay, none of the elements is balanced. So we're going to begin with carbon, right? Look like I have more carbon on the left than on the right. And the only compound that has carbon on the right is CO2. So I'll put a 3 in front of CO2. Okay, to make it 3 carbons. And of course I change the number of oxygen, right, as well. So 3 times 2 is 6, 7, 8. I have now 8 oxygen. Okay, carbon is balanced, but I still have to balance the other elements. So let's say for nitrogen, well, I have a N2 on the right, okay? And so one way to balance is if you put a coefficient of 3/2 for N2, okay? You'll be able to balance nitrogen, right? Okay? Or, if you don't like these fractional coefficients, then don't use it, okay? Use a full coefficient, use 3. So you put 3 in front of N2, 3 times 2 is 6, so now you have 6 nitrogen. And you only have 3 on the left, so you put a 2 in front, and that's going to balance nitrogen. Of course, you change the number of carbon. Now 2 times 3 is 6. So on the right, you need to change this to 6. Okay? And of course, you change also the number of oxygen. 2 times 9 is now 18. So you actually have 18 oxygen. Here you have 6 times 2, which is 12, plus 1, plus 1, so 14. Okay, so look like we get carbon and nitrogen balance in a hurry. And we still have to balance hydrogen and oxygen. But look like we can just mess around with the coefficient in front of H2O. Because, you have only 2 hydrogen, right? Actually, this is also changed. It's 2 times 5, it's 10 hydrogen. So if you put a coefficient of 5 over here, then that's 5 times 2, which is 10. Now you have 10 hydrogen. 5 times 1 is 5, plus 12 is 17, plus 1, that's 18. Okay? So it's a long process, but eventually you should be able to balance the equation. Okay? Part B asks you to calculate the number of moles of C3H5N3O9 in 1,000 grams of the compound. And I said in a hint that this has nothing to do with the balanced chemical equation. So part A is just the balance, right? Part B is actually to calculate if you have 1,000 grams of the compound C3H5N3O9. How many moles of the compound are you looking at? So it's actually a very simple calculation, compared to all the ones we've seen so far. Okay, so we need to determine the molar mass of this compound, which is 3 times 12, 5 times 1, 3 times 14, and 9 times 16. And I don't think I can do this in my head. So 3 times 12 is 36, 5 times 1 is 5.
Total of 227.
Okay, 227. 227 grams per mole. Okay, so what is 1,000 divided by 227?
It's 4.4.
Okay, about 4.4 moles. Okay, that's fine. And that's it. Part B is actually very easy. Just figuring out, okay, the molar mass of this massive compound is only 227 grams, and you've got 1,000 grams or 1 kilogram of the compound. So obviously you have more than 1 mole. In fact, you have 4.4 moles. Okay? Part C is a little different. Part C is another stoichiometry problem because it says assume that 1 mole of the compound is reactive weight. So I'm not assuming grams amount of the compound anymore. I'm assuming only 1 mole of the compound has reacted away. Okay? This is what you need to know. So which of the products is generated in the greatest amount? In both units of mole and in units of grams. Calculate both amounts. So what I'm saying is, okay, this is your limiting reactant. In fact, there's only one reactant. It has to be limiting. It is going to dictate how much product you will produce. Right? So let's assume you burn 1 mole of the explosive. Okay? And you have various products, like 3 moles of N2, 6 moles of CO2, 5 moles of H2O, and half a mole of O2. Which one is going to be present in the greatest amount at the end of the reaction? That's what I'm asking. Okay? And if you are really sure, if you're sure what's going on, then this is also a very easy question, because in the balanced chemical equation, right, you have 2 moles of the explosive reacting to form all these different moles of products, right? What if I only have 1 mole? So just divide this by 2. I only have 1 mole. Then you divide all these by 2, right? 3 and 3 halves. This becomes 3. This becomes 5 halves. And actually this becomes a quarter, 1/4. Still, okay, the balanced chemical equation tells you that, okay, 1 mole of nitroglycerin is reactive. You're going to form 1.5 mole of N2, 3 moles of O2, 2.5 moles of H2O, and only a quarter of a mole of O2. Which one has the greatest number? Is it a quarter, 2.5, 3, or 1.5? Well, look, this is 1.5, this is 3, this is 2.5, yeah, 3. So, yeah, it's a very easy question. So you're going to produce 3 moles of CO2, just because it has the greatest number, according to the balance equation. Of course, if you don't balance the equation correctly, then you will have trouble answering this question, right? So it all depends on, whether you can balance the equation. First of all, and second of all, whether you know what it means to balance a chemical equation. So now you figure out that you have 3 moles of CO2. This is the amount of product, okay, which is generated in the greatest amount. So 3 moles of CO2. And I also want you to express the same amount in units of grams. So for CO2, it's actually quite simple, because carbon is 12 grams per mole. 2 oxygen together, 2 times 16, which is 32 grams per mole. So altogether 44 grams per mole. It's 44 grams of CO2 per mole of CO2. And so the mole of CO2 would actually cancel. So it's just 3 times 44, which is 132, right? 132 grams of CO2. So you actually generate quite a bit of CO2, okay? If you burn 1 mole of the explosive, or if you reacted away 1 mole of the explosive. 1 mole of explosive is 227 grams, right? I think we calculated that before. So if you actually burn 1,000 grams of the explosive, you're going to get more products, okay, by about 4.4 times. So you multiply this also by 4.4, but that's not part of the question. The question only asks you to assume you have 1 mole, not 4.4 moles. Okay, assume 1 mole of the reactant, calculate the amount of product that is going to be generated the greatest in terms of mole and then in terms of gram. Okay? Let me see. H2O is 1832, yeah. Okay? So you generate the most CO2, 132 grams. Okay, so that's the end of the exam. So it took us about an hour and a half. No, actually it took us about 2 hours to go over. But I was of course, also describing the background of these different problems. So I mean, on the actual exam, I would expect, you know, that you don't need to be so thorough as far as the, you know, just describing or understanding the background of the problem. But I would say, you know, if you understand the background, your chance of answering a problem or solving a problem successfully is going to be enhanced by a whole lot. Okay, but a lot of the things I said, you could just, you know, kind of, you know, go through those in your mind. You don't have to write it all out. But, you know, for me to be writing everything out took us 2 hours to go over the exam. Anyways,